Welcome back. This is part 4 of week 2 lecture. In this part, we're going to have a look at what this AC induction motor catalog look like and learn how to choose a motor from a catalog. How do we make a selection? This is one page from the catalog and list quite a few motors that for our selection. The first column shows its output power. It goes from 0.18 then increase to 0.75. There will be more higher power motors afterwards. So you can see this catalog organizes the motor in its output power. The second column is its RPM. So it goes for each particular output power, you get 4 different RPMs, and this is corresponding to different number of poles the motor have. So for 2-pole motor, it will have 3000 RPM as its nominal speed, and 2740 is actually full load speed for that particular motor with 4% of slip. And also the motor, even with the same output power, it comes with different size. And from here you can also see that the slower RPM with the same output power, normally the frame size is bigger. And the reason for that is because if it's smaller RPM, means it will have a larger output power, and the size of the frame is actually more proportional to the torque than the power. If there's the same power, higher speed means a smaller torque, means a smaller motor. So if you look at this torque, it will have 4 different columns. The first column is the full load torque. So that's the Newton meter. That's the actual kind of loading you can have. Then it has 3 other columns with a locked motor, rotor percentage. So this number 330 is a percentage of that full load torque. It's 330%. And there's a pull-up torque, which is slightly smaller than the locked rotor torque. Then there's a breakdown torque, which is similar or higher than the locked rotor torque. So these 3 values all together actually combine to make up the run-up curve for the motor. So these 4 columns will give us information to choose the motor for the speed, for the size, for the torque, and for the output power. Additional column here is inertia. We remember when we design a motor, we don't just consider its normal working condition. We have to also consider how the motor start up. So in this case, this motor gives you maximum load torque, J over here. So J needs to be, say, for the first motor, it needs to be 0.022, needs to be less than that. Otherwise, the motor cannot be sufficiently start up. Those different torque values from the table at the right here, you can see I just make a copy of a very small portion of the table, actually can be used to make up this figure 7, the torque speed curve. You can see it's taken from the table with a percentage of the nominal torque. Some other motor catalog may not sort the motors by its output power. It might sort it by its RPM. So in this case, this table shows mostly all the 3000 RPM motors. You can look at the second column. They are all very close to 3000 RPM. So only difference is slightly different slip. But output power goes from 0.75 up to 55. You can see at the third column, the frame size of the motor become larger and larger with the output power. This is because when the RPM are the same, the output power is actually the same as the output torque, is proportional to the output torque. So the frame size actually is proportional to the torque in this case. And at the torque volume, you actually only see 3 columns here. the full load torque, that's in Newton meter. Then the other two is the percentage, the locked rotor and also breakdown. We don't have the other one run up torque. In this case, we're just assuming the run up torque is the same as the locked rotor torque. Also in that previous table, we don't have the load inertia in the table. So sometimes they put all those load inertia limit together into a separate table. This table actually can see the motor with different kilowatt and different poles, and all together that's the kind of load inertia limitation for all the motors. In particular, like in this red square spot, it's 1.1 kilowatt motor with 4 poles, and the limit inertia is 2.09 kilogram square meter. Other than the maximum load inertia and the longest starting up time, sometimes the motor provider will also limit how many times it's allowed to start up every hour. So for this example, with different number of poles and different frame size for the motor, it allows only certain times to start up. Say for this red square, it only allows this motor to be start up 20 times per hour. You can't just start, stop, start, stop, because that process is going to generate too much heat. The motor actually has its own protection mechanism by connecting a PTC element, which is kind of a resistor, but normally its resistance is very small. But when the temperature increases, its resistance can go extremely high. You can look at this blue curve. After the temperature gets to TNF, it goes like the resistance goes 100 times higher than the normal. So in that case, it can limit the current going through, kind of forcing the motor into a protection condition to stop the motor from getting too much heat and getting too hot. Also depends on how do you mount the motor. There's a few different options you can choose. We use the IM, that's a code from international standard, shows different way of mounting. There's a code with 4 digits, and the combination of those digits will show a certain meaning of the mounting method. Remember, this IM is for the mounting method. Also, the cooling has certain international standard. We use a IC code to define the way of the cooling, and it's followed with a number either 0 or 4. 0 is free circulation, means it's open the motor, and 4 means it's enclosed motor, so the surface cooling. And then there's a number 016, which defines a different primary cooling condition. Then there's a number from 0168 to define its like secondary cooling condition. Then these 3 numbers together defines how the motor is cooled. We mentioned before that the cooling is actually very important for a motor. If a motor can be perfectly cooled, then it can output very, very high kind of torque and current. The only reason is because when it generates too much torque, then there's too much current in the system, then it will generate a lot of heat. If the heat is not dissipated properly, then the system will be overheated and have to stop. IP is used to define the protection. It follows with 2 numbers. The first number indicates how is protection against solids like dust, other objects. The second number is used to define its protection against liquid, water, and moisture. So normally higher this number means the motor has better protection, can work in more severe or more bad kind of working conditions. Efficiency, we use IE to define the efficiency. It has 4 different classes, IE1 up to IE4. And each one of these class efficiency is not just one value. It's a value according to a certain output motor power. So if it's IE1 for like low powered motor, its efficiency is lower. For the high powered motor, the IE1 is actually quite high efficiency, because normally the higher power motor is more efficient by its nature. Also, there will be other information. I can't include everything here. One example is attitude and ambient temperature. So normally the motor is designed to work at certain latitude, attitude, and also certain temperature. If the temperature and the attitude changes, the output power of the motor will reduce. So there's some temperature factor, and the altitude factor has to be used to multiply on the motor power. The actual power will be slightly less. So you can see there's like 80 some percent. Say if it's a higher temperature, the power output will reduce. If it's a higher altitude, the power will also reduce. In Australia, we use IEC standard, that's international standard. In North America, they use NEMA standard. It's North America and the USA kind of standard. These two standards define things quite differently. They are interchangeable in some way, but be careful. Normally, in different countries, you have to make sure you choose the proper standard for your motor, following the proper kind of requirement from that country. So in Australia, normally we follow this IEC standard. Here are some useful links for you to kind of watch, to read about the motor. There are a lot of internet resources. However, the problem is basically there's too many resources. You don't know which one is actually useful for you. That's why we kind of have a short list for you, so make things easier for you to select those resources. And this is the end of all the slides for week 2.